us make a list of the factors that might influence the values of the gravitational force and the electromagnetic force between two objects. Since the gravitational force appears when the objects have mass, the gravitational force might depend on the values of the masses involved. The exact relationship between the gravitational force and the factors that influence it will be discussed in subsequent lectures, but let us say, for the time being, that the greater the mass of m1, the greater the gravitational force it can exert on m2. Also, the greater the mass of m2, the greater the gravitational force that is exerted on it by m1. Each mass exerts an attractive force on the other mass, and the direction of the forces are along the line connecting the centers of the objects. The distance center to center between the objects also has an effect on the gravitational force. The greater the distance, the smaller the gravitational force. With real objects, the distribution of the mass within the objects would need to be taken into account. But since we are only considering objects that are point-like and ignoring their shape, we will assume that all their masses are located at their centers. Now, for the electromagnetic force, I have already mentioned that this force is present because of a characteristic of particles called the electric charge. For example, if object 1 has an excess of 1 electron compared to its number of protons, and object 2 has a deficit of 1 electron compared to its number of protons, then object 1 would be negatively charged and object 2 would be positively charged. There would be an attractive force between object 1 and 2. In the case such as the one I have just described, increasing the distance between the two objects would also decrease the magnitude of the electric force. The velocity of the charged object will matter when dealing with the magnetic force, but we will deal with this aspect of the electromagnetic force in the last unit of this course. Finally, the distribution of the charged particles within the objects will influence the electromagnetic interaction between macroscopic objects, even if the objects are electrically neutral. Let us return to the subject of the gravitational force. It is present between any pairs of objects with mass. For example, there is a gravitational force between you and a chair that you're sitting on, between you and the moon, between you and the Andromeda galaxy. The total gravitational force exerted on you should, in principle, be the vectorial sum of the gravitational interaction you have with all the masses in the universe. A daunting task. However, we can approximate. Each contribution to the total gravitational force exerted on you depends on the mass of the other object and how far it is from you. So the largest contributor to the total gravitational force on you is from the closest, most massive object around. So it is from the Earth. As viewed as one big object, the chair you are sitting on might be closer to you than the center of the Earth, but the mass of the Earth compared to the mass of the chair makes the contribution of the Earth to the total gravitational force much bigger than the one from the chair. Also, the contribution of the Earth to the gravitational force on you is 1,600 times bigger than the gravitational force on you exerted by the Sun. So for objects at the surface of the Earth, we usually only keep the contribution from the Earth and neglect the contribution from the Sun, the Moon, and the Andromeda galaxy in establishing the total force of gravity exerted on these objects. The gravitational force exerted by the Earth on nearby objects is called their weight. The variable name we will use for the weight is Fg. With this approximation in mind, the weight of an object at the surface of the Earth is a vectorial quantity with a vector towards the center of the Earth, a direction usually referred 2 as downward. Note that downward in Sydney, Australia is not the same direction in space as downward in Toronto, Canada. I have already mentioned that the gravitational force depends on the masses involved and the distance between them. So for all objects at the surface of the Earth, their weight depends on the mass of the Earth and its radius, if we assume that the Earth is a sphere. Each kilogram of matter at the surface of the Earth will have the same magnitude of weight. So, a 2 kilogram mass will have twice the weight of a 1 kilogram mass. The weight of an object is proportional to the mass of the object. Let us call the constant of proportionality G. G has a value of 9.8 Newton per kilogram for object at the surface of the Earth. As we will see later, it is not a coincidence that it has the same value and variable name as the magnitude of the free fall acceleration that we had worked with in our study of projectile motion. A contact force is not a fundamental force. It is just a name that we give to the special vectorial sum of all the tiny electromagnetic interactions between the atoms of one object and the atoms of another object when the two objects are touching. But what is meant when we say that the objects are touching? Touch is an interaction at short distance. The distance is so short that the electrons near the surface of one object are repulsing the electron near the surface of the other object. The sum of the electromagnetic forces result into a net repulsive force that offers resistance to the intermingling of the atoms of the two solid objects. Bumpiness of the exterior surfaces of the objects at the atomic level will also offer resistance to the sliding of the objects against each other. Take, for example, a book lying on a table. The repulsion and the resistance to sliding could result in the following contact force exerted on the book by the table. We will label this force as Fc. When the contact is through exterior surfaces involving at least one plane, it is customary to split this force into two forces to deal separately with the two aspects of the contact force. The repulsion part is taken up by a perpendicular force to the plane. That is called the normal force, labeled Fn. The word normal here is not used in the sense of typical or usual, but with the meaning of being perpendicular. What is left of the contact force is parallel to the surface and is called friction. A lowercase f will be used in the variable name for the friction. The normal force and the force of friction are such that when added, they give the contact force. We will pay special attention to contact forces where the contact is through surfaces that are planes. However, there are also other contact forces, in the sense that they are summation of electromagnetic forces without planes involved. The force of tension, for example, involves a stretched rope. Notice that the quantity called tension is the magnitude of the force of tension. We will label it Ft. The direction of the force of tension exerted on an object by a rope is along the length of the rope. Buoyancy will not be really studied in this course since we are concentrating on solid objects, but in situations involving water, the upward force due to the water will be labeled Fb. In any other situation where the method of contact is not clearly specified, for example, when there are no planes touching, no rope, or no water, in these situations, we will call the contact force an applied force and label it Fa. Another special sum of forces is the net force. This quantity will have a special relevance to the motion of an object. The net force is the vectorial sum of all external forces exerted on an object. This definition requires a clear understanding of what is included in the object that you are interested in. Once you have established that, the forces between any part of that object and any mass that are not part of the object are called external forces. This is in contrast with forces between different parts of an object. Those will be called internal forces. Take the example of two boxes linked by an horizontal rope of negligible mass that are being pulled towards the right along the floor through the use of an horizontal rope. Let us consider that the object we are interested in consists of the two boxes and the rope that links them. They are both close to the earth, so their weights are external forces. We are neglecting the weight of the rope between the boxes. The force of tension that the rope in front of the yellow box exerts is an external force towards the right. Both boxes are touching the ground, so contact forces are present. First, we have the normal forces that make the floor repulse the boxes. Next, we have the frictional forces that oppose the sliding of the boxes along the floor. A drawing that shows all the external forces on an object as labeled arrows with their proper directions is called a free body diagram. The net force is the sum of all these external forces. Note that this net force is valid only for the object consisting of the two boxes and the rope. If we had been looking for the net force on the red box only, the sum would include the weight of the red box, the normal force on the red box, the friction on the red box, and the force of tension due to the rope between the two boxes. This last force was an internal force in the previous situation, but it is an external force when the object is the red box only. For the last item of this lecture, let us do another example of a free body diagram, the one for a book being held against the wall by an horizontal applied force. Here is the wall, here is the book, here is the applied force. I hope this is obvious that this horizontal applied force needs to be towards the wall in order to help keep the book in contact with the wall. The book is in contact with the wall, so there is a normal force perpendicular to the wall. Since this book is close to the earth, there is a downward gravitational force. The gravitational force would have a tendency to move the book downward. A frictional force is required to resist the sliding of the book along the wall. This drawing is the free body diagram required. Now that we have defined the net force on an object, we can ask ourselves, what is it used for? Newton will give us an answer. We will also have a closer look at the factors affecting the gravitational force that we have hinted at in this lecture. This will be the subject of the next installment.